Okay, and then in addition to this form of the chain rule, let's check Wikipedia, which is the chain rule here, and let's go to higher dimensional ones, and let's take a look at this, which is slightly different. So let's just take a look at this one also. So in this one we're saying z is a function of x and y and y are functions of t. In this actually more general version in Wikipedia, we're going to say z is a function of x and y. Actually, we're going to take it a little bit more generally there as well. We're going to say z can be a function of a bunch of things, not just x and y. It could be like three or four, whatever. And then each of these x can be a function of many things as well. So x is actually a function of a vector of different variables. So that looks like this here. So instead of z, they're using the outside function is y. So y is a function of not just x and y, but this and another thing and another thing and another thing. That's what this means. And then the u's inside are not just a function of one thing, not just a function of t, but they are a function of a number of different variables as well. So it's a function of here, and then another one, and so on. So in that case, instead of partial and non-partial derivative, which we have here, partial and then non-partial, we get partial and partial. Because when we talk about the derivative of u with respect to something, it's not, u is not just a function of just one thing. For example, here we had x is just a function of t, but in this case we don't have that. So instead of writing the full derivative, we write the partial derivative here. Okay, so we are here. So this is that scenario, and this is the same formula that we just saw on that other page, on the Wikipedia page. So we have this. So we have that p, and we're asking for the derivative of p with respect to a, but we do that by taking the derivative of p with respect to the intermediary variable q sub I of a, and then the derivative of that with respect to a. So this is the Wikipedia page formula. And in our case, we want the derivative of the loss function. Oops. So we want the derivative of the loss function, which is here. So we want the derivative of the loss function, so we want the derivative of, if we call it p, the derivative of p, and we want to do that with respect to the output layer in this case. But in between that, we run into the pre-activation layer. So we're going to say that it's the derivative of the loss function with respect to the unit layer, the output layer, is we can take the derivative of the loss function with respect to the intermediate pre-activation layer, and then the derivative of that with respect to the output layer. Now, we're going to need this in a second, so just to remind you of the notation Wij. So Wij is being used to indicate the weight going into the ith neuron from the jth input. So we're going from j to I. Okay, so try to remember that we're going from j to I, not I to j. So here we have this, we want the derivative of the loss function with respect to the output layer, output activation layer, HK. So that's with respect to here. So this is the neuron, this is the output. We want the derivative of the loss with respect to that. So here, we can see that if we're asking how does, basically derivative asks how does this change when we change this, but we're going to have to sort of consider how this, the change here affects this node, and then how that affects this node. That's the chain rule. But of course we also have to do it this way as well. So how does, because when this changes, this also changes, and that affects this. So in other words, we have to go through every, even though we're just doing from this node here, so this is the jth node in layer H. So anyway, it's just one node. But still, we have to consider all these nodes here. So that's why we have sigma I here. So in other words, we're going to figure out this path. In other words, when we change this, this changes and then this changes. But also plus, when we change this, this changes, so this changes, and so on. So we're summing up over all these nodes, so that's sigma I. So if you stare at this, you can see that this is the chain rule that we just showed from Wikipedia. Okay, now the next thing is, let's work on this piece here. So we're not going to work on this piece yet, but we're going to work on this piece here. So this is the partial derivative of A, which means the activation here with respect to a change here. But remember that A is given by this equation here, and this H here is the same as this H here. Okay? So if we're taking the derivative of A with respect to a change in H, basically all we get is this part here. So that's how we end up with this from here. And earlier, although I said it was kind of practice, we actually showed that this is this. But this is in vector form, whereas this is the summation form. Okay, so the next thing we want to consider is taking the gradient instead of the derivative of the loss function. So in the last screen we took the derivative of that, but now we want to take the gradient. So the only difference is, instead of this term, we're going to have the entire matrix here instead of just this column here, like this. So we'll have the whole matrix here, and we have the gradient instead of the derivative. Okay, so then the next screen is that we want to take the loss gradient at the hidden layers with respect to the pre-activation that is here, whereas last time, in the previous screen, we did it here with respect to the activation layer. So we did it here. Now we're going to do it down here with respect to that.